done like right now is the busiest time. Okay, enough whining. And did it let to record, right? Okay, good. All right. So today we are gonna do a really fun thing. The fun thing is called symmetric matrices. Like at first it might seem to you that symmetric matrices are just like another very special case, right? You were before dealing with the special case of square matrices, and even then I said that not all square matrices are actually diagonalizable even in the complex domain. So that looks like this, like not like ugly when you have like lots of exceptions, right? Like when you are coding things and like you need to worry about lots of cases, you know, that's always not nice. But it turns out that symmetric matrices, not only they occur very often naturally in applications, we will be talking maybe today, maybe on Wednesday, about quadratic forms, which directly lead to symmetric matrices, and there's many other things that also directly lead to symmetric matrices. But even more importantly, symmetric matrices, believe it or not, they will help us tame the general case of the rectangular matrix. So if we will want to do the analog of eigenvectors and eigenvalues for a rectangular matrix, right now we have no idea how to do that. Right now we only discuss the square case with eigenvalues and eigenvectors. But for a general matrix like this, m by n, m rows and columns, what can we do about, oh, you know what, I need some light. I was thinking, why so dark? It's because I don't have this light on. So if I have a rectangular matrix like this, then what I can do to analyze it, I can look at ATA, which is what? Which is a matrix. So AT would be n by m, so this would be n by n matrix, right? And also AAT, which is a matrix from m by m, right? And it turns out that these matrices, this will essentially be the idea of singular value decomposition, which we will cover, I guess, in the, if not the next lecture, then the next lecture. The idea being that these matrices capture a lot of the structure of A, but they are square and they are symmetric, which is cool, right? Obviously they are symmetric. If you do ATA transpose, you get AT and ATT, but that's just AT, right? So you get back ATA, so this is symmetric. For the same reason, AAT is also symmetric. So this is to show that symmetric matrices are really important. And even more importantly, they have beautiful properties. Essentially, the corner cases go away. So let's take a look at that. So as I said, for a general square matrix with real entries, we can find n eigenvalues, and sometimes there's always n eigenvalues. That is for sure. I was like confused because you know that there might not always be n eigenvectors, but eigenvalues there is always n of them. The catch here is that they might not be real. They might be complex, and if they are complex, they come in complex conjugate pairs. Remember that? Some matrices are deficient, so that means that we cannot find a full set of eigenvectors. We don't have full complement of eigenvalues. I think this was supposed to mean eigenvectors actually, so let me read this. So a deficient means they does not have full complement of eigenvalues. This means eigenvectors. And cannot be diagonalized. Yeah, that's true, right? Like we had some examples like this matrix, you cannot diagonalize it. It's just one of these deficient matrices. Now here is the good news. With symmetric matrices, all these problems go away. I guess that's really the pragmatic reason why they are so important. That we don't have to worry about these corner cases. So if we have a symmetric matrix, by the way, symmetric matrix automatically means it has to be square, right? Because if it's defined as the A transpose is A, so like if A was rectangular to begin with, m by n, then A transpose is n by m, right? So there is no way that they could match, although the shape doesn't match, right? So if this is matrix like this, the A transpose is a matrix like this. If A has to be equal to AT, they must be square, obviously. Whether they must be more than that, but they must also be symmetric along the main diagonal. That's really the idea of this. So, for example, matrix like this is not symmetric, but a matrix like this is symmetric. Right? Because the transposition for a square matrices, I can look at it as flipping the matrix along the main diagonal, like graphically. Yeah, you know this. So it turns out that if I have a symmetric matrix, and I'll probably be omitting the square because it's already implied. So it turns out that then you can prove that all eigenvalues will be real numbers. So the complex eigenvalues go away with a symmetric matrix. Very nice. From this fairly simply follows that all eigenvectors will be real as well. So in the case of symmetric matrices, you don't have to deal with the complex numbers. And even more than that, the problem of deficient matrices also goes away. So and there is even more than that. So for a symmetric matrix, the eigenvectors will actually be orthogonal. And there will always be a full set of them. For an n by n matrix, I will always have n eigenvectors, and they can be chosen to be orthogonal. Sometimes there is like a little catch that they don't automatically come out orthogonal, but you can always choose the eigenvectors so that they are orthogonal. So from these properties, we will prove some of this in a second, but you can summarize them in this theorem, which is sometimes called the spectral theorem, or I guess also eigendecomposition, a spectral decomposition theorem, that if you have a symmetric matrix and can be decomposed into an orthonormal matrix Q, a diagonal matrix lambda, and the Q transpose. And that's true for any symmetric real matrix. So that is really very nice. So let's take a look at why these properties are true. Let's start with the first one. And what we want to show is that the eigenvalues of a symmetric matrix are really real. No pun intended. So let's do this. This is like a proof. So we want to prove that if I take an eigenvector of the matrix and its corresponding eigenvalue, which in general might be complex, we want to prove that it in fact is a real number. Real numbers are a subset of complex numbers, right? So real number is both real and complex, but we show that if we just assume that it's complex, just from the fact that A is symmetric, we are able to prove that then lambda must be real, or the imaginary part of lambda must be 0. And how do we do that? Well, we take the complex conjugate, the lambda, this over bar means complex conjugate. You remember that, right? And we take a complex conjugate of the eigenvector as well. So this is a complex conjugate of the entire vector. It means conjugating every coordinate, every component of the vector. And because A is real and symmetric, then it doesn't change if we conjugate it, because it only affects the complex part. If the complex part is 0, doesn't care about the conjugation, and also doesn't care about transposition because it's symmetric, right? So we know that this is true. So we start with the facts with the equation of the eigenvalue and eigenvector. So because V was an eigenvector of A and lambda was eigenvalue, this is true. And because they always come in complex conjugate pairs, then we know that lambda complex conjugate and V complex conjugate are also eigenvalue and eigenvector, right? So this is also true. I guess this is true. You could just conjugate both parts and then say that A conjugate is the same as A. But this is what we discussed before. What you can do is then transpose this entire equation. So this transpose gives me V conjugate transpose A transpose, but A transpose is just A, right? So I can get rid of the transpose. and here it's V conjugate transpose lambda. Lambda conjugate is just a complex scalar. Okay? And then we dot product this equation with V conjugate. So if we do that, we get here. So I just took this equation and from the left multiplied with V conjugate transpose. This is what I get, right? Then I take this equation, which I have derived previously from the first one, and I multiply it from the right with V. That leads me to this equation. So V conjugate TAV times, yeah, that's correct. Lambda, this is just a scalar, right? So I can also write it on the left from it. Doesn't really change anything. So I have now these two equations, and look at them carefully. On the left-hand side is the same thing in both equations, right? It's V conjugate transpose AV here. There is V conjugate transpose AV here as well. So that means that these two things have to be equal, right? So, lambda V conjugate transpose V is the same thing as lambda conjugate V conjugate transpose V. So this right-hand side equals this right-hand side, because the left-hand sides are equal, so the right-hand side have to be as well, of course. Now, what is this thing? Again, it's the same in both, right? And that's just the vector conjugated dot producted with itself. So it means that in every component, in every coordinate of that vector, there will be a real number, right? Because if I have a complex number z, then the complex conjugate z times z is a real number. Right? Do you remember that, or shall I elaborate on that? So I take it as a yes. So that means that the V conjugate transpose V is a real number, and it's also non-zero because remember V was an eigenvector, and we are not allowing zero vectors to be eigenvectors, right? We have discussed that quite extensively. So this is not allowed by the definition. So this is just a scalar. It's a real scalar, and it's a non-zero scalar. So I can as well divide this entire equation by it. And what I get is that lambda equals lambda complex conjugate. That's what I wanted. This means that lambda must have zero imaginary component. In other words, lambda is real. Okay, that's the proof. And the only thing we have used here is that A is symmetric. We used it here that the transposition did not change A. If the transposition did change A, that this of course could not be true. Okay? Now if we have real eigenvalues, it's relatively simple to just realize that we have also real eigenvectors. So we have already shown that there are real eigenvalues. And how are the eigenvectors defined? Well, they are vectors, non-zero vectors in the null space of A minus lambda I, right? Those are the eigenvectors. There has to be at least one non-zero vector there, because that's how we picked the eigenvalue lambda. Sometimes there could be more than one. Now, of course, if because A is real and lambda is real, that's what we have just shown, that all the eigenvalues will be real, then of course this entire matrix is a real matrix. So there's no complex business whatsoever. So of course the null space will also be just real vectors, right? The complex numbers did not enter there in any way. So of course the eigenvectors, because they are in the null space, which is a real null space, they will also be real. So this is nice, the complexity, again forgive the pun, goes away. Alright, and the last thing we will show here about symmetric matrices, and there is some more to show, but I will not do all the proofs, I just don't want to keep it just purely math. But this one is good. this statement says that if I have a symmetric matrix and I have eigenvectors corresponding to different eigenvalues. So what I had before we had a similar statement, right? It's always very good to think about all these claims or the theorems and how do they relate to each other. So before we said, before we had a general matrix and we had eigenvectors corresponding to different eigenvalues, and we said that they are what? Certainly not orthogonal, right? We didn't talk about orthogonality before at all in the context of eigenvalues and eigenvectors. Before we said that if I have a general matrix, if I don't have symmetric matrix, then we showed that the eigenvectors corresponding to different eigenvalues must be linearly independent. It cannot be the case that one would be just like a scalar multiple of another, for example. Right? So for symmetric matrix, we can say much more. We can say that these eigenvectors are in fact orthogonal. So let's take a look. How can we prove this? So my assumption is I have a symmetric matrix A, and I have eigenvalue eigenvector pair, and I have a different eigenvalue eigenvector pair, such that the two eigenvalues are different, that lambda 1 is different from lambda 2. So what does that mean? So I can take the second equation here and dot product it with V1. So this gives me that V1 transpose AV2 is V1 transpose V2. But then I can look at the first equation here and I can dot product it with V2, or like multiply from the left with V2 transpose. And there I get V2 transpose AV1 is V2 transpose lambda 1 V1. So these here is like a similar story as before. Here I have V1, the dot product of V1 and V2. And because A is symmetric, then I know that these terms will be the same. So V1 transpose AV2, I can transpose the entire thing. This is just a scalar, right? So scalar equals its transpose. The scalar is the funny case of a 1-by-1 matrix. So if you transpose 1-by-1 matrix, the transposition does nothing to it. And we can write it using the product rule for transposition as V1 transpose. Here should be A transpose, but A is symmetric, right? So the transpose goes away. This is just A. And here is just V1. So this shows that this guy is actually the same as this one, thanks to the fact that A is symmetric. So we are in a similar situation as before, because the left-hand sides, this and this, are equal, and of course these two things are equal too, right? And of course, if I have V2 transpose V1, that's the same thing as V1 transpose V2. Again, by the same argument, right? I can just transpose this thing. This is just a scalar, so transposition does nothing to it, and it's this. So what does it mean? So what we get here, so I can write this as V1 transpose V2, and if I put it all on one side, because these things are the same, then I have this, right? Lambda 2 minus lambda 1 times the dot product of V1 and V2 must be 0. But because we assumed at the beginning that lambda 1 is different from lambda 2, that means that this thing is not 0, right? So the only way this equation can be true, and it has to be true, is that this is 0. This must be 0. There's no other way we could satisfy that, right? And V1 transpose V2 being 0, well, that's equivalent to the fact that V1 and V2 are orthogonal. Okay, so this is showing that if I have a general symmetric matrix, and I take eigenvectors corresponding to two different eigenvalues, then these eigenvectors must be orthogonal. Is that clear? Good. So far we have a proof of the spectral decomposition theorem. Maybe I should spell it, write it explicitly once again, because it's a very important theorem and called also spectral decomposition. It's another type of matrix decomposition, essentially. We already had some examples of matrix decomposition. We have been doing QR decomposition and LU decomposition, right? So the spectral decomposition is another type, very important, and it works for a square symmetric matrix, and it says that then there is a matrix which is orthonormal and lambda which is diagonal, such that the original input matrix can be written in this form: Q lambda Q transpose. So far we have proven this theorem for the case that the eigenvalues in lambda are all different. In this case, we already know from the previous so first of all, we already know that everything has to be real, that the eigenvalues and eigenvectors must be real. We also know that if the eigenvalues happen to be all different, then the eigenvectors, we already knew that for a general matrix, that then they are linearly independent, that they form bases. But by the previous theorem, by this one, we know that because it's a symmetric matrix, then the eigenvectors will also be orthogonal. So I can write them into an orthogonal matrix. So in the case the eigenvalues are all different, we have a proof of this. It's also possible to prove it in the general case when there are repeated eigenvalues. And this is what we will not do here because it's a little bit more technical. If you want, you can find it in the textbook. Gilbert Strang has it there. But it is also true. The only catch with the repeated eigenvalues, I mean, if there is like, if I have eigenvalues like lambda 1 being lambda 2, all being 1, for example. So this is the case of repeated eigenvalues. The only thing I need to be careful is that the eigenvectors don't automatically be orthogonal, but I need to pick them, make sure that they are orthogonal. I can choose them so that they are orthogonal, but they don't have to be automatically. In other words, I could pick an eigenvector basis which would not be orthogonal, but I can also pick one that is orthogonal. Okay, so this is the spectral decomposition theorem for symmetric matrices, and we will look at some applications. So one very natural application where symmetric matrices naturally appear is quadratic forms. First, do a little bit introduction here. Quadratic forms. You know what are quadratic forms? They are just multivariate degree 2 polynomials. So it sounds scarier than it is. What it means in R1, this just means a quadratic, like a hyperbola, quadratic function, where a is some coefficient, some real coefficient. Now, multivariate means that we go to more variables. So I can have a quadratic polynomial of 2 variables, x and y, and it would be x squared plus by squared plus cxy. And I'm just putting the degree 2 monomials. not including here the linear terms, even though you could also potentially include them. So ABC here are just real coefficients. So of course I can also go to R3. I would have 3 variables here. So I can do this, by squared plus cz squared. How many terms will I have there? Just to make sure you're awake before I write them down. 6, yes. So I'm picking all combinations of 2. Why is that? So those are examples of quadratic forms in 1D, 2D, and 3D. So how would this generalize to Rn? Clearly, I don't want to be like writing it out like this all the time, right? So I want to write down something nice. This is actually the real power of matrices. That matrices let you deal with this indexing, like this enumeration thing. Which, like sometimes there are like tools like you can do like this, right? Like when I have like 1 plus 2 plus n thing, so I just use this thing. Or you can have the sum notation, right? And matrices are essentially another way to hide the indexing, which is very nice, because then just everything becomes much simpler to manipulate. All expressions become simpler to manipulate. So what do you think, how would it look like in R to n, the general quadratic form? The idea is the same, right? In R to n, I will have n variables, x1 to xn, and I want a purely quadratic multivariate polynomial. These guys. So you could clearly write something like this, right? Lots of hand waving and lots of these what's this called? Oh, lots of dots. But we can write it elegantly using matrix multiplication. Do you have an idea? So it's gonna be some matrix vector multiplication, right? These guys A, B, C, and here D, E, F, they're just constant scalars, right? They pick a particular quadratic form. The variables, that's the like my unknowns or something. Those are the X, Y, Z. So those vary, and the A, B, C, D, E, F, whatever, they are constant. So in the general case, so if I say that I have a vector x, just these components, I make it back transpose. I could also write a column vector. I always assume column vectors by default. Then the general form of a quadratic form, there's another pun, so forgive another pun, is this. So I take a matrix, guess what dimension, n by n matrix, right? And this is the general form. So this is for if x was 3-dimensional vector, I would get exactly this. If it was 2D vector, I would get exactly this. Now here comes the point. It actually is sufficient to assume symmetric matrices here for A. Because, well, let's take a look at the 2D example. So let's assume x is just a 2D vector, so it has coordinates x and y. So in this case, my matrix is 2 by 2 matrix, right? So it looks like this. And here is my vector x, y. So what is this? This is x squared times a11 plus xy a12 plus xy a21 plus y squared a22, right? But these things are the same. So this really is just x squared a11 plus xy a12 plus a21 plus y squared a22. I have to copy that. So it turns out all that really matters for the quadratic form is the sum of these elements, right? So it doesn't matter if I take a matrix like this or a matrix like this, because in both cases the 2 and 4 sum to 6 and 3 and 3 also sum to 6. So if I do a quadratic form like this, and I do another one here, oops, this is something different, then I get exactly the same quadratic form, because these things just sum together. So it doesn't matter how I split them between the two. So I can as well just split them equally, right? That seems to make as good sense as anything else. And if I split them equally, that's equivalent to saying that A12 is equal to A21 in the case of 2 by 2 matrices. We can use an even split rather than some other arbitrary split. So that means that we can assume that I can say without loss of generality, A is symmetric. This is exactly what the without loss of generality means, right? If I just restrict myself to symmetric matrices A, I'm not losing anything. Because I can always, if I started with a non-symmetric matrix, I can as well redistribute it symmetrically, and I still have the same quadratic form. Or degree 2 polynomial. And this is true for arbitrary size matrices, n by n matrices in general. Okay. So now we know that these matrices are symmetric. Then we can apply the spectral decomposition theorem, right? And we know that we have n real eigenvalues. Maybe they are repeated, but certainly they are real, right? And now we can do an important classification of types of quadratic forms thanks to the spectral decomposition theorem. And here is what the classification looks like. You might have heard those terms before because they are useful in many contexts, mostly like optimization. Positive definite, negative definite, positive semi-definite, negative semi-definite, indefinite. Have you heard this mantra before? Good. So you will certainly hear it later on. So this is a classification of quadratic forms. I guess we will here concentrate on the 2D examples because they are intuitive to visualize, but it works in general n-dimensional space just as well. So I said that for quadratic form we can get away with a symmetric matrix. Symmetric matrix has n real eigenvalues, right? And then we can classify them to these 5 categories. So the positive definite quadratic forms are those where all eigenvalues are strictly greater than 0. And I'll show how they look like, the images, because then I think in 2D I can actually visualize it, right? In 2D, these quadratic forms are just mappings from R2 to R, so I can visualize them as a height field. So I will show you in a second when I'm done with this how do they look like. Looks like a valley. Negative definite, it's like the exact opposite of it. All the eigenvalues have to be negative. And now positive semi-definite, it's just a slight relaxation of positive definite, and it says that all eigenvalues have to be greater than or equal 0. So the only difference is that I'm permitting zeros here in semi. That's why the semi. The same idea with negative semi-definite, there they has to be less than or equal than 0. And the really interesting or really distinct case are indefinite matrices, which have both positive and negative eigenvalues. So the way you can classify these forms and is by looking at the eigenvalues and seeing to which category they fall. They always have to fall into exactly one of these. Well, I guess could say that positive semi-definite is also positive definite. That positive definite also positive semi-definite, but naturally you just classify it into the least most restrictive one. So let me show the some sort of poor man's visualization. My point is just to get across the idea, not to do the most beautiful pictures. So as I said, if I have a general quadratic form, I only need symmetric matrices here for A. And if the matrices are 2 by 2, then we can just visualize it as a height field, right? Here it was like cropped, so we can actually see something. So don't mind the boundary here, that's arbitrary. But the really important point, what I want you to remember, is for positive definite, you get a convex function. It looks like a bool, or like a valley, or whatever you want. Negative definite is like the opposite shape. If you like turn it upside down, this thing, so it's like a peak. And the cool case, and sometimes problematic case, is the indefinite one. The indefinite, what does it mean, being indefinite? So it means I have some eigenvalues which are positive and some eigenvalues are negative. So there will be eigenvectors corresponding to these eigenvalues, right? And in the eigenvectors, and they will be actually orthogonal in the case of symmetric matrices. So in one direction, in the direction corresponding to the eigenvector corresponding to the positive eigenvalue, I will have something convex like this. And in the direction of the other eigenvector corresponding to the negative eigenvalue, I will have something concave like this. Oh, by the way, are you familiar with these terms? Convex function and concave function? There is convex sets and concaves. Well, there is no concave sets, I think. There's just non-convex sets. But for functions, there is convex function and concave. So convex function means that if I draw a line, then the line is above the function. And concave means that f is concave if and only if minus f is convex. So if I flip it and I get convex. So this is for functions. So like don't be it's something slightly, it's very closely related, but you need to differentiate between convexity for sets and for functions. So here I was talking about convexity of functions. So this is a convex function, this is a concave function, and in this case the quadratic form is neither convex nor concave. You can just say it's non-convex. This is the problematic case quite often. You might have heard that there is like an entire field of optimization called convex optimization, because these convex functions are very important optimization, essentially because all the algorithms in optimization that are robust and guaranteed to work reliably in all cases are only for the convex cases. And for a quadratic form, you now know how to verify if it will be a convex function. All you need to do is compute the eigenvalues and test if all the eigenvalues are positive. Oh, maybe I could also make a mention what means the semi-definite case. What do you think would the semi do to these pictures? It's a good sort of exercisey thing. Would be what?
It wouldn't be tangent to a plane that's on zero.
It wouldn't be tangent to a plane that's...
Wait, the semi-definite include zero or they don't?
The semi-definite does allow zero, yes. So yeah, I think what you meant is that in some direction, the function will essentially be flat, will not be changing. And that's exactly right? So I guess you can imagine this like a bent, maybe I can do this here. See, like this. Maybe I could have drawn a picture for that too, but I guess you can imagine it, right? Like if I take this and then I translate it, right? So in one direction there will be nothing changing, but in another direction it will be convex or concave, depending if it's positive semi-definite or negative semi-definite. Okay, here is another fun thing we can do with the quadratic forms. We can also understand them by looking at their level curves. So those are lots of points such that the value of the function equals some chosen c, where c is just some chosen like iso level or something, and I'm looking for all the points x which satisfy this equation. Those are called level curves. Like if you know it on the map, right? What is the name of these curves on the map? Iso lines or maybe
Like elevation.
right, elevation 1.
Yeah. Maybe it's ISO. Because they're all the same.
I know there's like isobars, and for the idea is the same. It's always level curves. So it's a level curves of altitude. That's what you normally have on the map, right? Like if you are hiking, you want to know if it's like steep uphill or steep downhill. So that's why it's there. So for we can look at the level curves for quadratic forms too, and depending on the type of quadratic form, we'll be looking at different types of curves, or in this case, they are called conic sections if we are dealing with quadratic forms. And here are the cases. The type of curve is determined by the type of the quadratic form. So if we have positive or negative definite matrices, we will get ellipses or circles. Circles are just special cases of ellipses, right? We will get hyperbolas for indefinite matrices. Guess what we will get? That's sort of missing here for the semi-definite matrices. When one of the eigenvalues is, some of the eigenvalues are zeros, at least one. There is another bola. For semi-definite, you would get parabola. Yeah, this also works obviously in higher dimensions, but we'll be looking just at the 2D example. Oh yeah, and I'll show you the 2D example of for the ellipses. The ellipses sort of are most intuitive cases. So let's look at the classification here. You can also explain these curves as conic sections. So I take a cone. So this is like two ice cream cones glued together, the center. And then I can cut it with a plane. So if I cut it with the plane in such a way that I only cut one of these cones, one of the halves of the cone, then I get a parabola. If I cut it in such a way, and it's of infinite extent. If I cut it in such a way that the curve is closed, then I get either ellipse or circle. That's in this case. And if I cut it in such a way that I get two open curves, then this is a hyperbola. And there's actually a very cool way how to tell which is which if I have the matrix. So if I'm in 2D and I have the matrix, I can write the matrix like this of the quadratic form. So those are my parameters. We said that it has to be symmetric matrix, right? And that these two terms are summed together, right? So this means that it just sums together to B, right? So I guess I could write it out. That this gives me quadratic form ax squared plus cy squared plus b xy, right? And the very cool thing is that we can, looking at the determinant of this matrix, we can characterize which type of curves we will be dealing with. So this is the case when the determinant of this matrix is 0. In this case, the determinant, the same matrix, is greater than 0. And in this case, the determinant of the matrix is less than 0. Now actually we can also tie it together to what we know about eigenvalues and determinants. You know that the determinant is what of eigenvalues? We will have two eigenvalues here, right? How do they relate to the determinant? We had it last time. If this matrix has eigenvalues lambda 1 and lambda 2, then this determinant I used to classify this is the product of the eigenvalues, lambda 1 times lambda 2, right? So in this case, it means that one of the eigenvalues must be 0 And in that case, we get a parabola. Maybe I should write it here, right? This is parabola. In the case that both eigenvalues have the same sign, so both are positive or both are negative, then I get a positive determinant. And that's the case when I get an ellipse, or a special case, a circle. And in the funny case that one is positive and one is negative, then I get hyperbola. And what is really nice that using eigenvectors, we can convert these curves into a normalized, very simple form, or understand their behavior by looking at the eigenvalues and eigenvectors of the matrix of the quadratic form. So let's take a look at that. So if I have a quadratic form with the matrix A is symmetric, by spectral decomposition theorem, I know that this Q and lambda exist, such that Q lambda Q transpose is the same as A, just the decomposition of A. And then I can write this, I can write X transpose Q also as Q transpose X, the whole thing transposed, right? So the point is that I have the same thing here and here, except that here it's transposed. So what it means is that the Q transpose is just essentially a matrix of a change of coordinates. I am changing from one coordinate system where X of coordinates X into a different coordinate system of coordinates Y. It's exactly what we were doing at the very beginning. We were like switching between coordinate systems. In fact, it turns out that I can always pick Q to be a rotation. So this change of coordinates will always be a rotation. So I'm afraid I will not have the time to finish all of it. Maybe let me explain why I can pick Q to be a rotation. So by the spectral decomposition theorem, we are only guaranteed orthonormal matrix, right? But orthonormal matrices can be either rotations or reflections based on the determinant, right? But it turns out that in the spectral decomposition Q, QT, you can always arrange things in such a way that Q is an actual rotation, not a reflection. That's because I can write this way, Q1, Qn, and this is a diagonal matrix of the eigenvalues, and here is Q1 transpose to Qn transpose, right? And this can be written as a sum of outer products. Lambda I, Qi transposed. So if it happens that I have determinant of Q being -1, that's a reflection, all I need to do is flip the sign of the Qn, right? If I flip the sign, so if I take, I don't know, Q hat n, which is minus Qn, then the Q hat, so the Q hat n, not hat, tilde, Qn tilde, will be the same thing as Qn tilde, simply because the minuses cancel. So I can just flip the last column and make sure that Q is actually rotation. So that means that this change of coordinates will always only be a rotation. I mean 2D rotation, obviously. Yeah, and I'm afraid I don't have the time to explain all of it, so I will resume there on Wednesday, explain you exactly how the quadratic form can be simplified when I take the proper the eigenvector basis. So I'll leave you with a little bit of overhang. Do you have any questions to what I said so far? I'm surprised you are still taking notes. I would like you could also like take the notes from YouTube later and here just enjoy the show. Or
But then I have to do that twice.
yeah, I know.
Prices may not, please. it helps to look back. Like you'll say something and then like, oh yeah, that's true. Because you don't remember things the first time you see it.
Right. The thing is that like always when I was taking notes, I could not do things. I follow the lecture and take the notes. So like it's difficult synchronization problem. Like, do I want to note it down or do I want to think about it? What he just said, right?
Yeah, there is that conflict.
Okay. Well, whatever makes you happy. Okay. So we'll continue this on Wednesday. Thank you.